Okay, today's lesson is linear regression. In the first lesson, we were learning about how to do the machine learning, what we are trying to achieve with machine learning, and so on. Uh, so this is one of the machine learning technique. It is actually one of the main fundamental statistical learning technique as well. When it comes to linear regression, it was born as a statistical learning technique, and later it was developed with more and more techniques like advancements, enhancements in linear regression with different ways, and it was used for as a fundamental technique for machine learning. Right, so in machine learning, this is kind of the one of the most basic learning technique because it has a highly theorized and it has a very strong statistical background. It is also a very fundamental statistical learning technique. Right? Because this is simple and it is simple to understand, and once you understand, because you can get in touch with the flavor of machine learning and statistical learning, I selected this as the first machine learning and statistical learning algorithm in this lesson, in this series. Right. So let's start by understanding what is regression. We have known a little about what is regression. So when it comes to supervised machine learning, uh, so what is a supervised machine learning problem compared to unsupervised machine learning? In supervised machine learning, we have labeled data, right? So I mean, there can be one or more X values for both supervised and unsupervised data sets. But when it comes to supervised machine learning, you should have Y values. That means labels. Right? Right. That means you should have a data sets that have labeled the dependent variables. So already existing Y values or the dependent variables are known as labels. Right? So because it should have executed some uh, task, or then you must have collected some natural data as the data set for supervised machine learning. Right? So that is the difference between unsupervised and supervised machine learning. Unsupervised machine learning, you will not have any dependent variable values or labels, but in supervised machine learning, you should have labels. In regression, is one of the two types of supervised machine learning. So we said one is known as classification. The other one is known as regression. Right? In supervised machine learning, there are two types. One is classification. The other one is regression. In classification, we have set of classes to be classified by looking at the input variables or the independent variables. In the regression, by looking at the independent variable, you have to find the relevant uh, continuous value. Right? You have to predict a certain numerical value looking at the independent variable. So that is a regression. Right? So once you have trained the model, you have to test it to see whether it is working correctly for unseen data. That means the data that was not used to train the model. Right? So that is the test data. And using if the model is working well for the test data, then you can use the model for other real world applications as well. Right? So first thing is you have to train the model with the labeled data. And once you have trained the labeled data, then you have to test it with the separate test data set, which is also a labeled data set. Right? And you can find how much the predicted values from the model are different from the real labeled labels in the test set, right? And if that is not too much, that means the model can predict sufficiently well as we expect, then we can use that model for real world application, right? So which means you can use it in the production environment, right? So using it in the real world environment means you can use it in production environment in the to get the value out of it, right? And anyway, right? So once you have trained the model, that is not the end of it. So you have, when that in circumstances are getting changed, you have to change the model and you have to change the data, update the data, retrain it again and update the model, and so all those things has to be done. But when it comes to just looking at the basic states that you have to fulfill, first you have to get the data set, then you have to train it, and then you have to test it, then you can use it for predicting the values in the real world, right? So the regression is that the y value is a continuous value, like the temperature, right? So by looking at for example, if you have the x values are like longitude and latitude of in the world, and like the rainfall in the last day or something. By using these few parameters, you can find maybe what would be the expected temperature mean temperature of the day, right? Something like that. By looking at the patient's health conditions like the obesity, BMI, body mass index, and the age, you can predict whether this particular patient would have a heart attack or not, right? So something like that. So that is a classification problem, right? So, but if you are going to predict value like say like the cholesterol level of in the blood, that is known as a regression problem, right? So in today's lesson, we are going to learn about a specific regression problem known as linear regression, right? So when it comes to regression, we can have one or more x variables, which are known as the independent variable, and you have a single y variable or dependent variable, right? So in regression, so what we are going to do, we have set of x variables, 1, x2, and xn, and we are going to predict the y variable, right? Y value. So I can't draw it correct. Nice way. We are going to predict the y value or the label out of these x variables, right? That is the idea. So its y value is a continuous value. So that is, when this is a continuous value, we call it as a regression, right? So in order to, when you have a data set, like when you have certain variables, x1, x2, and x up to xn, some independent variables, and you want to predict the value of the y, which is the continuous variable, now it is a regression problem. So now you have many machine learning algorithms that you can use to do the regression, right? There are different ways of doing the regression. In all of the cases, so because all the regression algorithms are supervised machine learning algorithms, so you have to train the data set with this particular algorithm. For example, the linear regression, right? And then you have to test it with the dedicated data set, the test data set, which is a proportion of data that we have allocated for the testing purpose. And if the accuracy value is higher than the value we expected, like 80%, 90% or somewhere, then you can use it in production. But there's not only one single type machine learning algorithm, but there are various types. And what we are going to do in the regression is that we are going to have a model, right? We are going to build a model. Say this is the model, so that it can input certain x values or the input variables or the features, right? Like x1, x2, xn, and predict the y value, right? So once you train this model, so how does this insight of the relationship between these x values and the y value, this function, that this relationship is kept in this model? How is it kept? So in this model, so this is the model, right? In this model, the insight or the intelligence or the relationship between x and y are kept in this model as a set of variables. Not say variables, we call these variables as parameters, right? There are certain variables in this model which we are going to edit, right, by training this machine learning model, right? So initially we may have set these values to like some random value or some zero or somewhere some amount, right? So then what we are going to do is we are using these x values and y values in the label data set, the training data set, and we are going to assign the values to these parameters in the model so that it can predict the y values accurately. So predicting the y values accurately means the difference between the real y value and the predicted y value given by y hat, right? So the first lesson we have discussed it. The real value or the ground truth value is known as the y value, and the predicted value from the machine learning algorithm is given by the y hat, and this value should be minimized for all the data points, right? So the training data set, we have, say like we have 10,000 data points. So this error should be minimum for all the data points. So how we are going to make sure? That means for some data points, this value may be higher. For some data points, this may be lesser. So how are we going to make sure that this parameters are set so that this value is minimized for all the data points? So we can get the statistics of this error, right? So this value, the first lesson we said that this can be denoted as epsilon or the error, right? So we have to make sure this error is minimized for all the data points. That means we can get like average of the epsilons for all the data points minimum, right? But if you take the exact, you get the error. Sometimes this may be this predicted value may be somewhat higher than the real value, or sometimes it may be lesser than the real value. So there can be plus and minus value. So if you take the average, it would be like maybe it's like 0, right? So there, this error value would not be affecting the this average epsilon would not display the correct error level of this model. So what we have to do is we have to take the, either we can take the absolute value of these error values and take the average, which is known as the absolute error, absolute mean error, or you can take the square of this error values. You take the difference and you take the square. So either it is negative value or positive value, like if the predicted value is lesser than the real value, or if it is larger than the predicted real value, it would have a positive error when you take the square for the square of the error, and by dividing it with the number of data points, so then you can add all the data points for. So these are this is for a single data point. We can get the error. We can take the square of the error, right? And then we can add the errors for all the data points. I equals 1 to I equals n, where n is the number of data points, and you can divide the total error from the number of data points so that you can get the mean or the average squares of errors, right? So this mean, average, or mean, or the mean square of errors is actually used for measuring the error level in this machine learning model, right? So this one, just forget this one, right? So this one is not related. So just okay. So now this is known as the mean square error, or the MSE for the model, right? For the given data set, this is the MSE. So you get the difference between the real values and the predicted values and take the square and add it for all the data points. That means we get the predicted values for all the data points and on the training set, and we reduce it from the ground truth value in the labels, right? So then we take the square so that we will not have negative values, and then we take the average. That means we add all the values and divide by the number of data points so that you will get the mean square of errors. So in this one we can get the mean. Here we can get the square. From here you can get the error, right? So mean square error can be calculated, and we are trying to reduce the error, this error in this model. So this mean square is not the only way to calculate the error level in this total error in this machine learning model. It is one of the way of calculating the errors, right? So mean square error is used for this linear regression in our in the today's lesson, right? So that is why we have explained about mean square error. This is what we are going to use, right? So what the machine learning model tries to do is it to try to approximate the relationship, or approximate the relationship between these x values and the y value in the model, right? Sorry, approximate the y values or the label values with the predicted values or the y hat values in the model, right? So these are the predicted values. So the model is trying to, so actually this is the predicted value, sorry. And this is the real y value. So this y hat is trying to be equal to, trying to approximate this real label value, and that is the objective of this algorithm. What we are doing is we are little by little we are changing these parameters so that this y hat is going closer and closer to the real y values, but it would not be exact y value because there would be inherently there would be an error with the model, because this is an approximation function that we are going to train, but it would become, we can make the error level minimized by optimizing these parameters with time, right? So let's see how to do it. So mathematically, what we are trying to do is we are trying to, so this is the approximated function or the machine learning algorithms can be given by f hat x, right? And what we are trying to do is we are going to approximate the y or the fx, right? To read that is for that we are trying to minimize the epsilon, right? Epsilon is actually the difference between y hat and the y, right? So by doing that, we are trying to uh, get the values for these parameters. So once we get the optimum set of parameters, then the regression is finished, right? Then we test it with the testing data set and we check whether this model is working sufficiently accurately, whether its accuracy level is sufficient, and then if it is yes, then we can use it in for real world applications. Right? This is all about machine learning. Right? So uh, this is all about the regression. Right? So when it is when y is a continuous variable, this is the regression. Right? So we can explain it in a different way as well. Right? In here you can see, right? So this is the predicted value y1 hat for a certain uh, x value, right? For a certain we take a certain x value. And let me clear this other value so that you will not get affected with this. Right? So say you get this x value, right? Sorry. Okay. Right. So now what we are going to do is we take this uh, we take this certain x value, right? And for that x value, there is a this model will predict a certain value, right? So this is the value predicted by the model, right? This is because this is the value predicted by the model. This is known as the regression model, right? So this is the regression model, and this is the its y values are the values corresponding to the values predicted by the model. For this x1 value, the predicted value is y1 hat, right? So the exact uh, value for this data point is y1, right? This is what the label says. In the data set, it says the y1, the value for this x1 data point, xy value is given by y1. But the model predicts it is y1 hat, right? So then there's a difference or there's an error, right? So this is the error, this is the epsilon, right? And so these are the red points are the data points, and while this is the regression model, right? So this is how we uh, try to calculate the error so that you can train the model, right? Uh, so linear regression is actually a specific form of uh, regression, right? It's not something. Okay, let me first clear this. Okay. This linear regression is actually a certain form of regression. Where in the earlier case, we have seen this regression model is a curve, right? It is a non-linear curve, but when it comes to linear regression, the linear term means that our model should be a straight line, right? So when it comes to two parameters, like when there's only one x variable and one y variable, that means we have to predict the continuous y variable using the continuous x variable. You can use simple linear regression, right? With that, what you are assuming is that the relationship between x and y are linear, right? You might have already learned about this equation, y equals mx plus c. So in the linear regression, we assume that the relationship between x and y, or the independent variable and the dependent variable, has a linear relationship, right? If we draw this data in a scatter plot like this, like given in the blue dots, right? We can assume that the data we can assume this relationship between x values and the y values is approximately a linear relationship. So we can use the linear regression machine learning model, or the statistical learning model, to learn this data set, right? If it is not linear, we are not going to use linear regression, right? So that is the first thing that we have to know. So in order to use linear regression, first there should be a linear relationship, right? And because it's a regression, the y value should be a supervised machine learning algorithm with the y value of in which is a continuous variable, right? So when it comes to any machine learning model, we said that either it's regression or classification. When it is regression, right? So what we have to do is we have to find the parameters in the model, right? So when it comes to this linear equation, y equals mx plus c, what are the parameters? Y and x are variables, right? So parameters are m and c, right? M and c are the model parameters. Right? So if you can use this data set given by the blue data points, and if you can find the optimum line fitting to these data points, which is this straight line, then our linear regression is successful, right? So in order to find so how do you say that you have find this straight line? You can say this straight line was found once you have found the values for m and c in this y equals mx plus c equation, right? So once you have find the values for m and c, you can say that you have you have trained the model, right? You have find the line when it comes to mathematical terms, or you can in the machine learning terms, you can say you have trained the model by finding the values for m and c. So m and c are the model parameters, right? So we have to find these m and c parameters so that these errors, the total errors given by the mean square errors, is minimized, right? So if you just take only a sum of the errors, it is not sufficient. You have to take all the errors. So in order to get to minimize the errors for all the data points, we are using the mean square error, right, which is given by the MSE, which I have just explained, right? And it's the number of data points. So now let's first look at this example, right? First, just look at this problem where it's asking, sorry, Sorry. Uh, what it says is that once you the problem is the investment company is looking for companies to invest, right? So there's an investment company which is using this machine learning model, and they are trying to invest, right? So what they are trying to do is they are trying to uh, find, they are analyzing the R&D cost or the research and development cost which related to the profit, right? For each of the companies. So like for this company, the R&D cost is this much and their profit was this much. For this company, the R&D cost was, for this company, the R&D cost was this much and the profit was given by the Y value, right? And how to model this? So you, by looking at this relationship, so this should be a scatter plot, right? So with this using looking at this scatter plot, at once you can see there's a, this is approximately a linear relationship, right? So maybe you can use this, the linear regression, to approximate this relationship and train a model so that it can get the values of the new R&D new company and set the R&D value, and they can, the investment company can predict the profit of this, of that particular company, right? So before we apply this data set, first thing you have to do is you have to do the exploratory data analytics first, where we have to clean the data, and all those stuff that you have to do, the pre-processing stuff, the data cleaning and filtering, outlier removing, and all those things, and then you can see the relationship between this R&D and profit using a scatter plot, and then you can apply the linear regression to predict the profit in the new company. Right? Okay. Now let's look at this one. So here what has done is, after creating using the linear regression, they have developed a machine learning regression line, right? So this yellow line is the regression line which is developed by the model. So finding this model is actually finding the values for M and C, right? In the Y equals MX plus C, this finding this yellow line means you have found the values for M and C for the training data set, right? And then you can use this this model with the testing data set, and you can find in the testing data set also, you can use either the mean square error or the R-squared statistic to find the whether this data set, whether this model is working correctly for unseen data in the real world, right? So unseen data means the data that were not used to train the model, right? So when you are training a machine learning model, you have to make sure that your model is working sufficiently accurately for unseen data. Unseen data means the data that were not used for training the model, right? So either you can use mean square error or R-square statistic, or there are some other variations of this R-square statistics, right? So we may be discussing them later, right? So you can use these things to find whether the test set is working sufficiently accurately for the test set with the developed model. And if it is yes, the answer is yes, then you can use it in production. Or if it is not, you have to maybe you can use some different machine learning model, or maybe you can look at the explorers data only. So maybe you can go to the beginning and you have to find a different data set, or change the data set, or change the quality of data, increase the quality of data, add some more data, or whatever it is to do the process. Right? Start the process from the beginning. And now let's see about multiple linear regression. Right? So in the earlier case, what we have learned is how when you have a single, so say you have a single data point known as x values, x1 for x variable, and there's only one y variable, right? But in real world, there are not only single x variable, then there can be multiple x variables, right? x1, x2, there are two x variables, that this would be a three-dimensional plot, right? If it is, if there are more than two variables, then we can't actually visualize this data in a graph or anything, right? So when it comes to a 3D plot like this, when you have two x variables, x1 and x2, this regression line in the simple linear regression that we have seen before, just few minutes ago, becomes a 2D plane, right? So now it is not a straight line. For a straight line, we have to find the M and C, right? M and C parameters. But now what we have to find is find other parameters relevant to flat plane, right? So when it comes to a three-dimensional space, we are not going to find the single straight line, but we are going to find the parameters relevant to a this flat plane, right? So this should be a two-dimensional plane, which represents the data points in this three-dimensional space, right? So this three-dimensional representation is known as the three-dimensional space, right? So when the data is represented in this 3D chart, our regression line becomes a regression plane of two dimensions, which should be a flat one because we are using the linear regression, right? So if it is a if it is just a general type of regression, it may be a curvy line, right? Not a flat line, right? But because this is a linear regression, this regression plane is actually a flat plane. So when there are two dimensions, x and y, x1 and y, we have to find the straight line. When it is a three-dimensional one, where x1, x2 are there against y, then you have to find the parameters for this two-dimensional plane. And if it is more than two dimensions, this plane is actually, if it is for example, if there are three dimensions, x1, x2, and x3, then this plane becomes a cube, right? So actually you can't see it. So these multidimensional planes are known as multidimensional hyperplane, right? So these are known as multidimensional hyperplane, right? So the dimensionality of this hyperplane is one dimension lesser than the total number of dimensions in this space, right? So in this case, there are two dimensions. So there are actually two dimensions, right? X1 and y. So this is one dimension. because there are 3 dimensions, x1, x2, and y. This plane becomes a 2-dimensional. That means 3 minus 1 dimension plane. And if it is if this space becomes an n-dimensional uh, hyperspace, so this kind of space is known as hyperspace when there are multiple dimensions. So this hyperplane is known as it would be having n minus 1 dimensions when there are n number of dimensions in this space. Right? So when the dimensions are greater than 3, actually greater than 2, actually you can't visualize it, but when it is 3, you can draw it in a 3D way. But when there are more than that, you can't actually visualize it. But you can intuitively understand that there would be a space like that, and you can use a regression hyperplane, a multidimensional hyperplane to as the regression model. Right? Okay, now let's delete them and move to the okay. So when there are only 2 dimensions, we call it as simple linear regression. And when that means there is only one x variable and one y variable. So when there are more than one x variables, like x1 and x2 and x1, x2, x3, and so on, we call it as a multiple linear regression problem. Right? So from here onwards, we are going to look at multiple linear regression problems. The plane, when it comes to simple linear regression, we said that we can represent it with say like we can represent it y equals mx, sorry, plus c, right? Sorry for my handwriting because I am using my unfamiliar hand. Sorry. So this is for simple linear regression, right? But for multilinear regression, this is the formula. This is the uh, hyperplane that we are going to use, right? Here, instead of using m and c for parameters, we are using the parameters as beta parameters, right? This instead of c, which is the constant value, we are using beta 0, which is a which is a scalar value, right? So, and these are the other coefficients, beta 1, beta 2, and beta n, right? Instead of m, right? Instead of m, we have multiple number of parameters. So beta 0 is the coefficient, is the intercept actually, right? Like the c. And beta 1, beta 2, beta n are other coefficients of this uh, hyperplane, right? These are the x values, x1, x2, xn. So this hyperplane can be represented as y equals beta 0 plus beta 1 x1, beta 2 x2, and beta n xn, right? And that is how we represent the hyperplane in the equation, right? Okay, now let's see what is beta 0 is the intercept, and for each index of I, this beta 1, beta 2, beta n, instead of 1, 2, 3 to n, we can use I as the index, right? Similarly, in general, we can call it as beta I, right? For all the other coefficients. For the first, for the intercept, we can call beta 0, and for the rest of coefficients, we can call it as beta I, right? So this I is between 0 and 1. N is the number of dimensions, right? So actually one lesser than the total number of dimensions, right? So okay. Uh, Before we do the linear regression, you have to make a serious set of assumptions, right? So you can't by just uh, any other any problem at your hand, which seems to be a regression problem, you can't simply use linear regression, right? So there are several assumptions that you have to make before you use this regression used with uh, using the statistical learning technique known as linear regression, right? So these are the four assumptions that you have to make. So we can actually check statistically whether these four assumptions are satisfied, and only yes, or if these assumptions are sufficiently satisfied, then only we can use linear regression, right? The first one is known as the linearity. Linearity is first assumption. The second one is known as the homoscedasticity of residuals. So don't get afraid, right? So this is a very simple term. Or simple it is known as the equal variances. So the x variable should, so this linearity means there should be a linear relationship between x and y. Simple, right? So earlier also we said, right? So by looking at the scatter plot, this data should be having a linear relationship. That is the linear assumption. And when it comes to homoscedasticity of residuals, that means uh, when you are having a relationship like this data points with the number of x values, the variance of this is the variance, right? The channel where these data points are distributed. So this should be fixed, right? This should not be like this, where with the value of x, the variance is increasing, right? So in this case, the variance is increasing or gets widened with the value of x, right? So this type of increasing or decreasing or changing variances with the value of x is not acceptable, or it violates the uh, homoscedasticity assumption. Now, autocorrelation means each of the data point that we have taken are independent from the values in the values in each data point are independent from the other data points, right? There's no correlation between the previous values and its previous values of x values is known as the autocorrelation, and there is no autocorrelation between the other values of x data points that we have taken, right? Have taken means within other data points, there should not be a relationship or correlation between the other values of x values with the number of x value, right? When you are increasing the x value in data points, these data points should not be depending on the earlier values. But when it comes to time series data, this assumption may not be holding, right? So in those cases, you have to make sure this no autocorrelation property is tested correctly. And also these errors should be right. So if this is the regression line, these errors should be having an error, right? So this is the x value, right? With the x value, these residuals or the errors with the changes with the real values should be having a normal distribution from the mean value, right? So these x values should be having a, or the residuals of the x values should be having a normal distribution. So that is the fourth assumption. So actually, we can look further into these aspects. So when you say linearity, what it says is that the dependent variable and the independent variable should be having a linear correlation, right? So when you plot the data using a scatter plot, you should be, so that's what we have, that's why we have learned the exploratory data analytics. In the exploratory data analytics, by looking at each of the x variable with other x variables, sorry, x variable with the y variable, for each x variable with the y variable, you should be having a linear relationship, and then only you can use the, then you can validate the linearity assumption, right? So the linearity is not the only way to check it. There are some other statistics, but simply you can use the scatter plot, right? If you see that there's no linearity, say like you see that uh, the relationship would be like where it is a x, it's like if it is x and x1 and this is, sorry, x1 and this is y, right? And if it is something like this, which is a superlinear relationship, maybe you can use a polynomial of x, like you can check with, not with x, but you can take the graph with x square and x1 square and y, and see whether there's a, maybe then there would be a linear relationship, although the x1 is not having a linear relationship with y, but when it comes to x1 square, it would be having a linear relationship. Then only we can use the x1 for linear regression, right? So in that way, you can transform these variables to a suitable format so that the x variables and the, or the independent variables and the y variables are having a linear relationship, right? So actually, not only the polynomials of x like x square and so on, you can actually use the exponentials, like you can take like say like e to the power sorry 2 to the power x, something like this, or you can use the logarithms if it is, if the correlation is something like this, you can take the log value so that this x value is having a linear relationship with y, right? So what you have to do is, so when this relationship between the x and y are not linear, you can use some transformation like polynomial of x and exponential or logarithm of x, so that the and create another feature or create another x variable, and you can use only that x variable in the linear regression to make predictions. But you can't use the original x value for predictions because they are not linear. So this is one thing you have to learn, right? The other thing is the homoscedasticity or the uh, residuals, or residuals are known as the errors, right? So the errors should be independent from the x value, right? That means, as I mentioned earlier, when it comes to x values, this error should be, error means the difference between the actual value and the predicted value should be having a constant variance when the x is increasing, right? So that means for all the values of x, the variance of this in each of this point should be, means the errors, or these are the errors, right? These errors should be having a constant variance for all the values of x, right? You can otherwise you may be using some other uh, regression techniques like weighted least square regression, where you can weight differently for different uh, sections in the x, so that some x values would be having higher variance of errors, some x ranges would be having a lesser number of errors, variance of errors, so that you can weight them accordingly for different x values, and that is known as the weighted least square regression. So you can use these kind of techniques, but you can't use the linear regression if the variance of errors are not constant for all the x values, right? So in order to check that, you can use this Bruce-Pagan test or White's test. So those are the some statistical tests that you can use for testing whether there's any, whether this this homoscedasticity is there or not, right? So if the homoscedasticity is not there, it is known as the heteroscedasticity, right? So with heteroscedasticity, you can't do the linear regression. So the other requirement is that the other assumption is that there should be no autocorrelation, also known as the, so no autocorrelation in residuals. Residual means errors, right? Or they should there should be a independence. That means each of the data point should be independent from other data point, right? So as I said earlier, when we take some time series data, if that means the data points are correlated with the previous timestamp, this assumption may not hold, right? So in that case, you can use some statistical tests to see whether this no autocorrelation requirement is satisfied, right? Autocorrelation means the x values are, whether we are checking whether these x values are correlated with its own x values. For example, if x1 is a variable, independent variable, you are checking certain all the values of x1 are correlated with the other x1 value, right? So this is a difficult task, but because of that, normally what we are doing is we are trying to find whether, when especially in the time series uh, cases, we check with for one timestamp data points. Like for example, when you take the timestamp t, we can check whether the timestamp t minus 1 is has any correlation for the value of t, right? So you can use that Derby-Watson statistic represented by D, right? So with this equation for all the time steps T, so that it can see whether there's any relationship or any correlation between the time step T minus 1 and T, right? If there's no correlation, this D value should be between 1.8 and 2.2, right? So if the D value is lesser than 1.8, there's a positive autocorrelation. That means there's autocorrelation, it is higher than 0, and if the D value is higher than 2.2, we call it as a negative autocorrelation, right? So because of that, we have to make sure that when you are doing some time series, maybe you can use a statistic like the Watson statistics and make sure it is between 1.8 and 2.2. And the final assumption is that the residuals are normally distributed. That means for all the x values, the residuals, that means the error values that you are having for all the x values should be having a normal distribution, right? So in the homoscedasticity, what we said was that the error values should be having a constant variance for all the x values. In here, what we say is for all the x values, the residual should be normally distributed, right? So you can actually use this QQ plot, which is a visualization technique, or you can use the histogram or KDE to visualize it with the or you can use statistical tests like Shapiro-Wilk test and Anderson-Darling test for checking whether these residuals are having a normal distribution in a sufficient level, right? Otherwise, you can't use the linear regression. So other than the given four main assumptions, when it comes to machine learning, we have to make sure there's no multicollinearity of data, right? So what is this multicollinearity? Multicollinearity is that each of the independent variables, that means x variable, should not be having any correlation with other independent variables. Say, for example, if you take x1, and if we have the x values x1, x2, and x3 as the independent variables, x1 should not be having any correlation between x2 or x3, right? x2 also should not be having a correlation between x1 and x3. x3 should not be having any correlation between x2 or x1, right? So the idea is that these independent variables bring new amount of information to the model, right? So when you draw the scatter plot, or by looking at the pair plot, you can easily see whether there's this multicollinearity, right? So where we plot with, for example, x1 and x2 in the plot, right? So if you can see there are some relationship, right? Like a linear relationship or something. That means both x1 and x2 are bringing the same kind of information into the model, right? But when it comes to training a machine learning model, you should not use the same feature with multiple names, right? So with x1 and x2. So if that is the case, either you can remove x1 or the x2 and use it with the rest of the variables. So idea is that when you have too many number of variables, that causes the problem of the curse of dimensionality, where your model's predictable capacity would be exponentially reducing with the number of features. Because of that, you have to make sure that you use the minimum number of features possible to have its ability to represent more, right? And if you are adding more features that are bringing the same information as the other features, that means you are uh, adding some noise into your uh, form of noise into your data set, so that your machine learning model would be having lower performance or lower accuracy once you train it. So when by looking at these kind of multicollinearity, right, that means looking at x1 and x2 and x1 with x3 and x2 with x3 and x2 with x1 and so on, you have to see the correlations, collinearity between all the pairs of variables and see whether if there's any correlation. If there's any high correlation, maybe you can remove one of the variables and see whether you can do it correctly, right? Or maybe you can use some other technique, like without removing, you can use some dimensional reduction techniques, like principal component analysis. So you can use some feature engineering technique so that you can uh, combine some of the features together to get a better feature. And you can, in that way, you can get a high quality feature and also reducing the number of features, right? So this kind of techniques can also be done, like feature engineering. And also you can remove some other features if they are not they are redundant, right? So this pairwise correlation can actually be visualized using a pair plot or a heat map, right? And this can, with the in statistics, you can use this variance inflation factor given by 1 minus R square, right? So we will in the next slide, we will explain what is R square, right? So with this one, this statistic, you can see whether there is any correlation, whether there's the multicollinearity between a given couple of uh, x values, right? Independent variable. So VIF is 1, there's no collinearity. If the VIF is greater than 10, generally it's problematic. That means we have to do something with the features by reducing it, or uh, dimension reduction or whatever it is, to uh, change to the features, because it is too much. For, for all the assumptions and this multicollinearity thing, you will find some amount of issues, but if it is too significant, you have to take action. So for now, let's see what are the so we will say, let us see what is the how to calculate R square. Before that, let's say now what you have done up to now is that you have you are going to train the model, right? So what you are going to train the model is that you are going to fit the given data set to a hyperplane defined by this equation, as I mentioned earlier, right? So in this case, you can actually see we have added the epsilon or the error term to the this linear combination, right, with the parameter values and the variable values, right? So when you say beta 0 plus beta 1 x1, beta plus beta 2 x2 plus and beta n xn, plus epsilon, right? So these are the values generated by taking this linear combination. You will have the approximated value for that data point, and you have to add the error to get the exact y value, right? So that is what we have represented here. So this can also be represented in the vectorized format like this, like xt beta plus epsilon. So xt is actually also a vector and beta is actually a vector of beta 0, beta 1, beta 2, beta n, right? So x1 actually you can see here, it starts with 1, right? So this 1 is therefore multiplying. So this is like the x0, which is 1, right? So multiply with beta 0, right? So in this case, we are using beta 1 x1, but in here, what it really happens is beta 0 x0. But instead of x0, we added the 1 for the x vector, so that x vector can be directly uh, uh, multiplied with beta 0, so that x1 can 0 can be directly multiplied with beta 0 to get the beta 0 and get this epsilon, get this linear combination, right? And then we add the error, and then you will get find the ground truth y value, right? So what we are going to do is we are going to find these beta I values, beta 0, beta 1, beta 2, beta n values, or the beta I values, by using the data set that we are given, and we are going to find these beta values, or we are going to actually find the beta vector, right? So how do we find? So what is the way that we are going to optimize these beta values? What we are going to do is we are going to minimize this mean square error, or this value, right? Or actually we can represent the same mean square error in this vectorized format, right? Where E is represented by yi minus yi hat, right? So this is given in the vectorized format. In either way, what you are going to do is you have to uh, change these values in beta vector, right? In this beta vector, so that this mean square error is getting reduced again and again, right? That is what we are doing during the training. So, what I have to do again and again is I am talking about the iterative methods, right? So, but there are two types of techniques uh, used for linear regression. One is the closed form solution, and one is the iterative uh, techniques. So in the iterative techniques, you have to uh, calculate values again and again, iteration by iteration, so that it would go to a optimum value. So this is a numerical technique, right? So it would actually not exactly go to the solution, but it would go near the solution. So one of these technique is widely used technique is known as gradient descent technique. So we will not discuss about this technique in this lesson, because we will be discussing it in later lesson, right? So, and the other technique is known as the closed form solution. The closed form solution means you don't have to do anything iteratively, but you can use a certain formula so that you can give these data points, the training data set for this function, and then you can calculate the beta value. So this is known as the ordinary. So the example technique is known as the ordinary least square technique, right? By minimizing the ordinary least square, the MSE, mean square error values, you can get the exact values for the beta parameters in a single operation, right? So you don't have to do any uh, iterative techniques. This is an analytical solution where you would have to do some matrix related calculations, sometimes matrix inverse operations as well, right? So which is a very computationally expensive technique, computation expensive task, right? However, if you can do it, you can calculate the beta values in a single step. But because when there are number of before that, even before you apply this kind of technique, closed form solution, you have to make sure that the assumptions, the linearity, homoscedasticity, normality, and the independence requirements are satisfied. Otherwise, uh, the error would be due to the error, this solution would be suboptimal. And because this ordinary square techniques can't identify or kind of eliminate some forms of noise. So this is prone to the errors that some of the errors that are due to the noise data, right? So it's not easy to remove the noise from these solutions when it comes to orderly square. And but the advantage is that when you have lesser number of parameters, like 2-3 parameters, then you can simply use, for example, for the simple linear regression, you can use this ordinary square technique and calculate the values for M and C, right? For the simple linear regression is very fast, right? But when the number of parameters are large, you have to do a very complex matrix operations, especially a matrix inversion operation, which is getting highly difficult or computationally highly expensive when it comes to when the number of parameters are getting increased. Because of that, these closed form solutions are not used when the number of parameters are too large, right? So when the number of parameters are too large, we are using these iterative techniques, mainly the gradient descent technique, right? The advantage of using the ordinary least square is that you for the smaller values, for the small number of parameters, you can get this fast. But in general, because our data sets are in our practical scenarios, we have a lot of x values. We are generally using this iterative technique, gradient descent technique, to uh, find to train a machine learning model, especially for this linear regression. Right? So when you evaluate in the model, so once you have trained the model, now you have got the values for the beta, right? So for the beta parameters, and now what you are going to do is you are using a dedicated train set for testing how accurate the data would be when you are predicting the values for the testing data set, right? And once you evaluate the testing data set, then you can use in production, right? So for the evaluation, you can use two techniques, mainly the mean square error value or the R-square value, right? So when the R-square is getting closer to the 1, it is better. Otherwise, it is not good, right? That is how we evaluate this method. The machine learning model, right? So this is how you calculate the R-square value, right? Because this is first you calculate the mean given by y hat, but not y hat, y bar, right? Y bar is given by taking add all the values for yi and divide by the number of data points. So that value, you know, that is the mean, right? This is calculated the mean. Mean is given by y bar, right? And you take the sum of squares known as the SS rest for the residuals, right? Residual sum of squares, residual sum of squares, right? So that is given by yi minus fi. Fi means actually this is the y hat I, right? Y hat I, and take the square and get the sum. This is the vector representation, right? And also you can calculate the total sum of squares, SS total sum of squares is given by yi minus y bar, which we have already calculated is the mean. Take the square and get the sum, right? So once you have calculated the sum of residual sum of squares and the total sum of squares, y 1 minus residual sum of squares divided by the total sum of squares, you can get the R square parameter, right? If the model is perfect and if it is so accurate, yi would be equal to the fi or the yi hat, right? And in that case, the residuals would be 0, right? So because this one would go to 0, this because our SS stress would be 0. SS stress when this is going to 0, this one R square would be 1, right? 0 divided by anything is 0. 1 minus 0 is 0. Sorry, 1 minus 0 is 1. So this R square would be 1 for the perfect model. This R square would go to 1, right? But in practical cases, this would not be the case. It could be lesser than 1, right? So up to now, what we have discussed how to use in the first we discussed how to use a single uh, independent variable like x1. Then we discussed about how can we use the multiple independent variables like x1, x2, x3, known as the multiple linear regression. And now we are going to see there can be some relationships which cannot be modeled with linear relationships with x. So what can we do, right? So in the earlier case, we said that in order to for the linearity assumption, we have to make sure that these x variables are linearly correlated with y variable, right? But say that you see relationship like this with the x for the x one independent variable with y dependent variable, you have a relationship like this. So this is not a so this is the regression line, the red line, but this is not a linear regression, right? Because this line is not a straight line. So if you want to get the regression line like this, which is not a straight line, you can use polynomial regression. That means you can use powers of x variables, not the one first power. Instead of that, you can use different powers of the variable, different exponents of the variable for the linear regression, so that you can do the you can make a model for nonlinear regression required, right? So first say that your x variable is not not having a linear relationship with y. But once you find that x square is having a linear relationship with y, then you can use x square. We have learned it, right? We have already said that we can use it, right? And also you can find that even x or x square is not having a linear relationship with y, but you find that x cube is having a linear relationship with y. Or you find that the x square plus uh, x cube is having a linear relationship with something like this, right? In that kind of scenario, we can create new features uh, by taking the powers of x, exponents of x, polynomials of x in higher degrees for making the prediction, right? So first we start with the x with the linear regression, simple linear, not multiple linear regression case. We can start with the first degree. That means we start with linear regression, and then we can increment the powers of x variables, and then we can increase one by one. Then we can go to the 2 and 3 and so on. And we can train like we did in the multiple linear regression scenario. And this is known as the polynomial regression. So this is an example, right? Where you have the x as the independent variable and y as the dependent variable. Right? Initially, we can start as having the first degree is x to the power 0, or x to the power 1, right? And you can get this. You can start with this equation where y equals beta 0 plus beta 1 x. Right? So in this case, where the x to the power 1 is used. And if this is not having not giving you the correct results, what you can do is you can add another x variable which is x to the power 2. So in here, make sure that what you are discussing is that you are starting with actually this is not a multiple linear regression. This is we are talking about simple linear regression, right? So we are only having a one x variable, and then we add the power. In the second iteration, what we do is we take beta 0, the same as beta 1x, that is there, and then we add the new term, which is beta 2 x square, another parameter, and x square. This is known as the quadratic form, and we find whether this can model the relationship of the data. If this is still this is not possible, we can add the third degree of the same independent variable, which is the same beta 0, beta 1x, beta 2x square, plus beta 3x cube can also be added. And then we can see whether you can predict it, right? When you add the number of polynomials, then you would have a higher chance of making of modeling the data set. But make sure that when you add too many polynomials with higher degrees, you would have some problem known as overfitting. So we will be discussing about these issues in future. But for the moment, that make sure that you should not be adding too many degrees, too much. You should not go to higher polynomials, and you have to stop somewhere, because when you are trying to test the accuracy of the model with test data sets, you would find that when you add higher and higher number of polynomials, your testing error is going to increase again, right? So because although this model can be fitting very well to your training data set, it would not be reflecting the reality, so that it won't fit for the real world data which we are going to test with testing data set, right? So the testing data set is therefore testing for the real world data, which is not used for training, right? So when you are using the testing data set, if the error is getting increased, that means we should not add more and more parameters, and we should stop, and we should find the model which is having the least error in the testing data set, right? So in the earlier case, what we have discussed was with using the simple linear regression with polynomial regression. And in this case, now you can use multivariate polynomial regression. That means you can have more than one x variables, and there also you can increase the degree of each of the independent variable, and then you can increase the accuracy by increasing the exponent or the power of each of the independent variable. So, And the problem is that when you are having many number of variables, like say like you have three independent variables, when you are adding a degree, an extra degree, like when you take the quadratic form, it would not be like it would be increasing the number of terms in your model in an exponential way, right? So, for example, so we will see how this is going to happen, right? So, when you are having too many independent variables, it would not be wise to uh, add the polynomials of each of these variables, so that you would not be able to manage the number of parameters with your computer. Your computing power would not be sufficient, and your memory would not be sufficient to calculate these things when you have higher number of variables, right? So this is an example, right? So suppose you have only x1 and x2 as independent variables and y as the dependent variable. Right? So the multiple linear regression problem, the model that you can create is something like this: y equals beta 0 plus beta 1 x1 plus beta 2 x2, right? This is the multiple linear regression problem. And so this is the polynomial to the power of x, right? So x1 to the power 1, x to the power 1. Right? So now when you go to the second degree polynomial, uh, it is the quadratic form, then see what happens to the model, right? So initially there are only 3 terms added. Now how many terms? 1, 2, 3, 4, 5, 6 terms, right? Beta 0, beta 1 x1, beta 2 x2, beta 3 x1 square, beta 4 x2 square, beta 5 x1 x2, right? Now see how many the number of parameters added when you increase the polynomial degree. So now if you add another degree, like when you go to the cubic form, actually I haven't given it with plus sign. I have just added the cubic form number of parameters, where you would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? So there are 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, there are 9 values that you have to calculate for developing this model. So when you increase the polynomial degree, it would be very difficult. It would become very difficult for calculating this model. So you should not go to a very large number of degrees when you are having large number of independent variables, right? But there are some heuristic ways that you can increase the number of variables, which we would be discussing later, where you can increase the number of variables with higher degrees, but we are not looking at all the possible features, but we may, by looking at only some of them, heuristically we can increase the uh, number of features by adding more and more features using higher order polynomial of the same feature. Say like first you can use x1, then x2, and then you can use x1 square, x2 square, and the combinations of all the 4. And then you can add another x1 cube and x2 cube, and then add the combination of all the 9 parameter, all the 6 parameters, right? And instead of looking at all the combinations, we can do some intelligent guess and see and do some assumptions, like when you find the good parameter, uh, the best parameter, that we assume we can do some assumptions, like then you have to do you have to add other parameters from the rest of parameters while keeping the best parameter in the model, right? And that means you are adding more and more parameters and so on. Or you can use all the parameters and then you can reduce one by one kind of thing, right? You can reduce, you can start with this kind of scenario and you can remove some of the combinations and see how the model accuracy is improved, kind of. So we will discussing these techniques later. So for the now, this is all that we have to do for the uh, linear regression, right? So this is about homework if you want to do. And if you have any questions, you can ask.